So the first thing we can do is we can try and look at the mass density. And in principle, what we'd like to do here is just add up all the mass. So you look at each star, you measure its mass, you add it to the list, and you add up all the mass within some volume, and that volume has to be big enough for the cosmological principle to apply. So you add up all the mass within a few hundred megaparsecs and see how much that is. However, it's not very simple because you can't identify every single star within 200 megaparsecs. There are 10 to the 11 stars in our own galaxy. There are many thousands of galaxies within 200 megaparsecs. You can't even see each individual star. So you can't do it like that. And so what you actually do is you measure the integrated mass via the integrated light. And that's a much more straightforward thing to do. So what I mean by that is if, for example, you take an image of the sky, and this is an image taken from something called the 2-Mass All-Sky Survey. This is a survey actually in the infrared that looked at the entire sky. Then what you see in this particular image is in the middle here, you have the Milky Way, and then all the other coloured things around you, they're all background galaxies. And so what you can do is you can measure the brightness of the galaxy and the redshift of the galaxy. And for this particular exercise, the redshift is a good enough approximation to the distance using v equals h naught d that it doesn't matter. This is not the precision distance measurement that we'll get onto later. And that gives you what you call a luminosity density. And that's the number, which is, for example, in this, 1.2 times 10 to the 8 solar luminosities. In this particular case, in the B band, which is about 450 nanometers per cubic megaparsec. And remember, a megaparsec is something like 3.08 times 10 to the 22 meters. So these are very big numbers. You have to worry about these, by averaging over very large volumes. And so in principle, you could just say, well, is every star like the sun? If that's the case, then this is easy because your mass density is then just 1.2 times 10 to the 8 solar masses per cubic megaparsec, because one solar luminosity equates to one solar mass. And the answer to that question, unfortunately, is no. There is a relationship between luminosity and mass. So the luminosity of a star scales something like m cubed. So that tells us that most of the light, especially true if we're looking in the blue, is from massive stars. I.e., a star that's 10 times as massive as the sun gives out not 10 times as much light, but 1,000 times as much light. So most of the light is coming from massive stars. And then you also have to look at what's called the initial mass function. And this tells us the distribution of number, dn, by unit mass. And it's proportional to m to the minus is important here, 2.35. Or at least down to some low mass end. So this is the opposite. So here, there are many more low mass stars than high mass stars. And the contribution of each and where you lie, of course, depends on the interplay between these two things. And you might think, well, 2.35 here and 3 here aren't so different. That's not so different from L proportional to M. And it's kind of not. You can work this out in more detail to work out actually what the mass to light ratio should be. And so, that's a not too bad a guess. In practice, and we'll set this as an exercise for you to actually show a little bit in more detail, the local star density is rho stars equals something like 5 times 10 to the 8 solar masses per cubic megaparsec, which is something like 0.004 rho crit. So stars do not provide the necessary critical density. Oops. Not quite sure how that happened. But stars aren't everything. Stars are not all the mass. You have dust, gas. You also have remnant stars. They are things without nuclear fusion, so white dwarfs, neutron stars, and black holes that have mass but don't have any light, or relatively little light for their mass. And if you add all of that together, there are various ways you can do that I won't go into, you can get what's called the Baryon density. And that's omega B, and that's equal to 0.04. So still, all the baryonic matter, all the stuff that you can see, all the stuff that's made up of matter that's familiar, is only about 4% of the critical density. And what you would probably initially conclude from that is that therefore the universe should be open. Right? It should just have an open, expand forever history. But it's worth looking at other things as well. And so having thought about what the matter's doing here, you might think about what the radiation is doing. And radiation is easy. And radiation is easy because we've just measured radiation right back here, just up here. This is radiation from stars. And you can immediately note, stars convert very little rest mass to energy. It's a fraction of a percent. So radiation from stars is not important. And so the most abundant photons in the universe are from the cosmic microwave background. And we know that there are about 10 to the 9 of those for every baryon. So actually that looks quite promising, doesn't it? Because omega baryon's 4% of the universe. So in fact, the photons are there's many more photons. But the energy of your baryon, well, most of the baryons are just protons, so it's mpc squared. It's about 938 MeV. On the other hand, your energy of your cosmic microwave background photon, which is at about, say, 100 gigahertz in frequency. This is why they talk about it being the snow you can see on your television. Not that any of you will remember when you could see snow on your television. But back in the olden days, your television used to have this fuzzy picture, which was partly at least cosmic microwave background photons. And they, of course, have an E of h nu, which is equal to 4 times 10 to the minus 4 electron volts. So the difference between this energy here and this energy here is much more than a factor of 10 to the 9. So radiation contributes even less than matter. And in fact, omega R is of order 10 to the minus 4.